Okay, in this video, we're going to be reviewing the basics of inverse functions, because soon we'll be looking at their derivatives. Okay, so recall that a relation is just what we call a set of ordered pairs. We usually have our independent variable and our dependent variable, or our x and our y, our input-output, or the domain and the range. Domain just means the set of all x values, and the range means the set of all y values. And then a function is a type of relation, specifically where each element of the domain, so every single input, is paired with the unique element of the range. So every x has exactly one y value. If we start talking about the inverse of a function, we can get that from switching the coordinates of each of those ordered pairs. So in other words, you're switching all your y's and x's. So if two functions are inverses, that means that if you plug one function into the other function, they will cancel each other out completely. So if you plug g into f and you plug f into g, either way you just get x back. That means that they are inverse functions. Okay, so a few little algebra notes. If g is the inverse of f, then f is the inverse of g. Okay, so it's just like division is the multiplication, or sorry, division is the inverse of multiplication, and vice versa. So the domain of one will then become the range of the other, and then the range of g would then become the domain of f. And not every function has an inverse function. Okay, that's very important. If g is in fact the inverse of function f, then another notation we can use for that is f with a little -1 that looks like it's an exponent, but it's not. It's understood that that notation means that it is the inverse of f. So just be really careful when we start looking at these, because the notation gets iffy. So that's not the same thing as f prime. A little -1 is not the same thing as f prime. One means inverse, the other means derivative, and they're totally different things. Okay, so geometrically, because you're just switching your x and y's, it ends up that your inverse function is a reflection of your original function, which is actually kind of cool. So if we have some function like this, there's a function f, and then I've drawn in here the line y equals x, okay? It passes through the origin, passes through 0 because that's the y-intercept is 0. It has a slope of +1, so it goes through like 1, 1, and 2, 2, and 3, 3, and all those points. So then f prime would look like this, where it is a reflection of f. So it has just been flipped over y equals x. Pretty neat. That happens because we have switched all of our x's and our y's. Okay, so if it passes through like 3, 3, for example, it wouldn't switch, but any points that are not on the line y equals x are going to move accordingly. So you'll recall from when you learned about functions that a graph represents a function if it passes the vertical line test. Well, in order to determine if a function has an inverse, once you've already determined that it is a function, it will have an inverse if it passes the horizontal line test. Okay, so for this, for example, it passes the vertical line test in that you cannot draw a vertical line through it and hit the graph more than once, but it also passes the horizontal line test. Any horizontal line that you'll draw through it only touches the graph once, and that's why it has an inverse, because none of the x's or y's repeat. When this happens, we say that the function is called a one-to-one function. Okay, so if it passes both the vertical and horizontal line tests, in other words, none of the x's repeat and none of the y's repeat, a function where there's no two domain values with the same range value. It's called a one-to-one function. And so if it has an inverse and it's one-to-one, both of those things go together. That's a if and only if thing. Okay, so every one-to-one function has an inverse because it passes the horizontal line test. Another term for this, if your one-to-one function, generally speaking, these are going to be either increasing for all x or decreasing for all x. And if that's the case, we say that it is monotonic, which is kind of fun to say. So we say that a function that's always increasing, like a linear function, for example, is always increasing or always decreasing. We say that it is monotonic. Or if it's only doing that on a certain interval, we'll say it's monotonic on that interval. Okay, so here is an example. Suppose f is strictly monotonic. Okay, so we know that it's either always increasing or always decreasing. And continuous. Okay, use the chart below to answer each of the following. Okay, so if we are looking at things that have to do with, that's supposed to be the eraser and that's not erasing. Okay, so if we are looking at f inverse, remember that f inverse just means to switch x and y. Okay, so for example, if we want to know f inverse of -6, that means that we're going to look at where y is -6 here, and that means that f inverse of -6 is equal to 8. So in other words, it's like you're plugging in y and getting out x. You're going just backwards now. Okay. Man, my pen is, there we go. That's better. Okay, so f of 2 is like normal functions. F of 2 means that 2 is x. So f of 2 equals -1. Okay, so that's Algebra 101 right there. Okay, so f inverse of 2 means that now 2 is the y, so f inverse of 2 is equal to -1. Look at that. Now, here's the thing. Because a function and its inverse cancel each other out, if this next one says f of f inverse of -10, then we automatically know that it's just equal to -10. Another way of thinking about it is you start on the inside function. F inverse of -10 is 10. Then we would take f of 10, which would just take us straight back to -10. That's one reason why a function and its inverse strictly just cancel each other out. All right, now the next one though is f inverse of f inverse. So because it's the inverse twice, it's not canceling out. So we just start with f inverse of, so we're going to start on the inside. So we've got f inverse of, so we're starting on the inside with this f inverse of 2, which is equal to -1. Then we'll find f inverse with that new input of -1. So if we plug in -1 to the inverse, we get 2. Okay. The last one here, again, because it's f inverse of f, the order does not matter. They cancel each other out whenever one is plugged into the other. So we automatically know that those cancel each other out and we just get the -6 back. And again, the reason that is happening is because you're taking -6, you're plugging it in for x, and then you're getting it back out. You're taking the y, plugging it back in, and you're just switching back to x again. Okay, so that's very basics with functions and their inverses. So let's look at one more. Okay, if f of x equals 2/3 x plus 5, g of 4 equals -2, and g of -2 equals 3, without determining the inverse of f, find the value of f inverse of g inverse of -2. Okay, so first of all, just a note on the notation because you have not seen this in a while. That whole f inverse of with that little o, we have been writing that with our chain rule like this. This is what it's really asking you to find, okay? That little like open circle notation means this. You're going to take g inverse of -2, then you're going to plug that into f inverse. Okay, so let's start on that inside piece. If we need g inverse of -2, that means that -2 is like the y. And we know from right here that if g of 4 is -2, then that means that g inverse of -2 is 4. So we've already gotten that first piece. Now we just need to find f inverse of 4. Well, okay, so if we're trying to find f inverse of 4, here's the thing. We have f of x right there. And if we want to know what happens if you plug 4 into the inverse, that means that 4 is like the y in f of x. So all you have to do is go back up here and just say 4 equals, and use 4 as the y value. 4 equals 2/3 x plus 5. So when it says without determining the inverse of f, that means without actually figuring out what that function would be. But we're still allowed to use that f of x in order to find f inverse. We're just not figuring out f inverse of x in terms of x. So here we'll subtract 5 from both sides. Multiply both sides by the reciprocal, and you'll get that x is -3/2. And that's it. To check this, now I will just show you, since it's not here in the slides. Here's how you find f inverse of x. And check. Well, okay, that does not look like it says the word check, but I assure you it was supposed to. This pin, tell you what, it's something else. Okay, so here's how you find the actual function, the inverse function. If we have f of x equals 2/3 x plus 5. First of all, we replace that f of x with a y. Switch notations. Then all you do, you transpose the x and the y. You literally just switch them. So now it is x equals 2/3 y plus 5. And you take that and you just solve that for y. So x minus 5 equals 2/3 y. Then you multiply both sides by the reciprocal. Y equals 3/2 times quantity, x minus 5. And to be honest, I would just stop right there in terms of finding that is f inverse of x. Okay, once you have that function, then you can just plug in this 4 from up here. Remember that came from the inside. If you plug that in to your f inverse, you should get that -3/2 back out, and indeed you do, because you get 3/2 times 4 minus 5, that's so you get negative 3 over 2, and there it is again. Okay, so to find the inverse function, if it's something simple and linear, just switch x and y and resolve it for y, and that's your inverse function itself. Otherwise, as always with these, start on the inside of when you have composition of functions, and then just realize it's just the same thing backwards. And from that, just take that, plug it in for y, and just solve for x. So it's basically just like they're giving you y instead of giving you x.